Thanks, everyone. Hello, yes, my name is Frank. I'm a systems modeling engineer, and I'm here with some of my team from Eutelsat. And I'm going to quickly explain who we are, what we do, and how we've adopted Julia to simulate the present and future of satellite communications at Eutelsat. So firstly, some marketing slides. Eutelsat is a satellite communications network service provider. We're operating fleets of 34 geostationary satellites and over 600 low Earth orbiting satellites in our OneWeb constellation. This makes us the second largest constellation in space right now. We work with a global network of partners to connect customers and communities globally, from communities in remote locations to in-flight connectivity. And being both a LEO and a GEO operator, we're one of a kind in the satcoms industry, uniquely positioned to help bridge these digital divides. So Eutelsat has been around for over 40 years. A big part of that legacy has been providing video services to over 6,400 TV channel customers, as well as GEO connectivity services. More recently, Eutelsat merged with OneWeb, our LEO constellation, and looking to the future, there are many things on the horizon, so replenishment and optimization of our first generation OneWeb satellites, options for innovation in multiple cutting-edge technologies, and looking even further to the future for our next generation constellations, such as IRIS², which is a European sovereign multi-orbit constellation that we're currently developing. For those who aren't aerospace engineers, what is a GEO, what is a LEO? A geostationary satellite orbits at a specific altitude such that it orbits the Earth every 24 hours. This allows it to essentially look at the same point of Earth at all times. Being far away means it can cover a large amount of the Earth, but it also introduces some latency as you have a longer path for the data to take. So this is great for things like TV broadcasting, but not so great for things like video calling, responsive web browsing. LEO satellites are much, much closer, offering high-speed, low-latency connectivity, like what you might get from your Wi-Fi at home. The issue with being much closer is that you need many, many more satellites in order to provide global coverage. So here's an overview of what our system kind of looks like. You can see we have a range of terminals. These can be on a plane, on a ship, fixed on a pole, on a car. And these terminals are interacting with our GEO and LEO services, which bridge the gap to our terrestrial ground network and ultimately our customers' connection points to their network and the internet. As systems modeling engineers, our main goal is to model the end-to-end system. So this is vital if we want to understand our system performance, things like coverage, service availability, system capacity, and our customers' user experience, like their data rates and their latencies. The important thing is that these are emergent phenomena. You cannot determine these metrics by looking at any one part of the system or by doing one single model. You need to model the entire end-to-end from user to satellite to ground and each subsystem along that path in order to get the insights. In order to get the insights, we need to make an assessment of our system or make a proposal for system optimization. So if we want to validate a new antenna in our system, assess commercial opportunity, determine what your ping would be in the mid-Atlantic on your flight, we need this end-to-end model. So we need antenna models to understand RF performance. If it's a mobile terminal, we need mobility models. For the satellite, we need models for orbital dynamics, the payload, its beams, the platform, its power. We need link budgets and RF models to link between the users and their satellites and our ground network. We need to model the brains, the systems and algorithms that calculate and allocate traffic within the network, as well as resource management of the beams themselves. And that's just the things you can see in this kind of simplified diagram. Many other things, service plans, what we offer, RAIN models, inter-satellite links, multi-orbit solutions, and many more. So why Julia? I know this is JuliaCon, so I am preaching to the choir, but deciding to shift from MATLAB, which is where we all kind of had expertise as engineers, so something new was quite a big decision. When deciding on how we would build this framework, there were these three main things that we kind of really cared about the most. Performance, Julia's quite performant. We were impressed with its simulation time for complex models. We needed a language that was familiar to engineers that are coming from MATLAB or Python, a kind of intuitive, expressive language that could allow for rapid prototyping of models and algorithms. And third, open source was a big factor. So avoiding licenses and toolboxes while having access to a library of incredible packages made by some of you guys. And that's why we decided to build our next-gen simulator in Julia, which is called Asgard, the analysis for subsequent generation architecture and development. It's built to be as modular and adaptable as possible. We have multiple current systems, multiple future systems. We needed to be able to simulate a range of different scenarios and subsystem combinations, different models at different fidelities. And just to take you through kind of like how we would use this, it's 3 main sections. So our scenario definition, this is defining the simulation scenario, some combination of input models and submodels. It could be the users, their locations, demands. We could use generated data, modeled data, or data from our live system. The constellation design, link budgets, ground network, any combination of these can be saved as a module, hypothetical system.jl, for example, and can be used as the basis for any future simulation. And we'll use that module to kick off our simulation. Within the simulation, we're propagating the constellation using Satellite Toolbox, performing any satellite maneuvers. In this new constellation state, we can call our subsystem entities. These are analyses and the submodels that are called in a kind of hierarchical fashion. We also have probe entities. So these are kind of like when we're wanting to do an analysis, these kind of sit inside the simulation, perform analyses that can get logged to DuckDB. And we can step through this, either let it run and then perform post-processing analyses and plotting afterwards using a plotting library we use Mackie. And finally, just because I think every presentation needs a cool animation, here's an example of how we would perform a simple global geometric analysis of satellite elevation for our hypothetical system and visualize it. So we can just create a simulation object using our system defined system module. We can inspect the simulation entities once it's been set up. Whole lot of preparing a figure for plotting and animation, and then just stepping through getting the new satellite states and performing some geometric analyses, resulting in this cool animation that you can see of a hypothetical constellation. And thanks.
Hi, thank you for the presentation. Do you also cover optical communication?
Optical, so
like for example, in your intersatellite links and things like that, or you just direct on that? Okay,
for that as well.
Okay, and have you compared the IDU models with like actual weather measurements in regards to how that affects your modeling accuracy?
I don't think we have. I'm not quite sure.
Okay, thank you.
Sorry.
Yeah, thank you for the talk. I just wonder when you are simulating the whole system of how these satellites operate, how do you replicate and simulate user behavior? For instance, if everyone wants to use the satellite services at once, it could overload the system. So how do you take into account such usage peaks into the model, because you can't know necessarily in advance?
Yeah, exactly. That's something that we have kind of like demand models for. So we can either like assume the worst case, assume a 95th percentile case based on like the data that we have recorded on our live system. We can make forecasts. We can introduce variability temporally to see how that affects our system.
Okay, one last question. Yes. was wondering if you have any tips for other people who want to migrate maybe from MATLAB to Julia for these like large simulation type work.
It's difficult, yeah, because we found that it's kind of similar, a similar kind of language. But yeah, there's a lot more that you have to take into account in terms of like performance. You're not caring so much about vectorization as you would be in MATLAB if you're trying to make it performant. I think the switch has gone kind of well. We've got a really powerful system. In performance, yeah, I think like in some models, like orders of magnitude faster, especially when we're really trying to have high fidelity models that we're kind of pushing to get as performant as possible and like really going deep inside the Julia. Definitely a lot faster. Yeah.
I am the colleague of Frank in charge of some translation of the previous version of the model from MATLAB to Julia. And to be crystal clear, MATLAB is a rather good toolbox, but not as good as NumPy. With toolbox which are very expensive, and the core language of MATLAB is simply flawed. MATLAB is by some lot of aspects the Visual Basic 6 of technical computing.
Some people have very strong opinions about MATLAB.
Just have a look on Rosetta Code. I began to write some reports on the comparison of the language. The first example I took was the exception handling between MATLAB and Julia. MATLAB use a global variable containing the last expression, while Julia, Python, and so on have a more serious exception handling. And we could continue for long, but I think the MATLAB story is a proof that even people who design a great toolkits, designing a proper programming language is one of the hardest tasks of computer science. Thanks a lot.